Okay, so now we have a sort of idea of what sort of formalism we can use to represent the description of the evolution of a plant throughout time. But we don't know yet how to make the map between plants and computational or mathematical objects that would represent the plant. So how does this work? So we said before that the plants, basically, they are modular structures. And these modularities, they can occur at different scales. So for instance, here on the picture, you see that you can consider a plant as a set of leaves or a set of internodes. But you can also consider the plant as a set of axes, or you can consider a plant as a set of layers of leaves like this, or you can consider a plant as a set of crownlets that populates the space. Actually, if you want to represent a plant in a sort of conceptual way, you would have three main means. First, you consider the plant embedded in the space. And then you say, my structure is actually the grid representing my space, where I consider that each square or voxel that intercepts a vegetal element is a vegetal pixel or voxel. And then my plant is represented by this set of voxel corresponding to the vegetal elements. A second idea would be to say, okay, I know the geometry of the different elements. I forget about the details of how they are connected with each other. I just need to know where they are in space. And this would be a geometric interpretation of the plant. I don't pay attention to the connection with everything. So I just removed also the trunk structure and then say that, okay, there is distribution of leaves in space. And this would be interesting, for instance, if you want to compute the amount of light intercepted by the plant. You don't need all the stuff, the trunks and the stems. You just need to know where are the leaves. So this type of representation would make a certain meaning depending on the application. And the final and more elaborate point of view is to say, okay, I want to represent all the organs of my plant instead of representing voxels, for instance, with their shape, etc. But in addition, I want to represent them and how they are connected with each other, their physical connection. So this adds an information that we call the topology of the plant, topological information. Okay. So the good thing that when we think about the things in this way is that we can make the abstraction that we are seeking. So for instance, if we take the geometry representation, then what I need to know is to have, for each of the component, a list of leaves. I need to have the position of the component, okay, and a matrix that will describe the orientation of the components in space. Okay? So that's it. The ID or the type of the component, leaf, fruit, stem, where it is, X, Y, Z, and in which orientation it is located in space. On the other hand, if I want to represent the topology, what should I use? Where? Here there is a notion in mathematics that is very convenient for this, which is notion of graph, where each element of the plant, let's say that I have branches mainly, are represented by a node in my graph. So a graph is a set of nodes and edges, usually written in this way. Okay. So this is a set of node, and this is a set of connection between the node. So here this would be a node I, and here this would be a couple ij for two nodes, saying that node I is connected with node j. And if I have node k in the system and I don't find this in this set, I don't find ik in the set E, it means that there is no connection between the element I and k. So and graphically, you can represent the connections in this way. T1 is connected to B5 because there is an edge between the two. T1 is connected to B3, but you see that B3 is not connected to B4. Okay. A graph that has this structure, this type of structure, where you don't find any cycle. So if a graph with a cycle is something like this. Okay. This is a cycle. When I have a cycle, my graph is not a tree. A graph which has no cycle, like this, is a tree. I should maybe put another one here. You see that there is no cycle here, so my graph is a tree. Okay. So plants, because all the elements are tied to just a parent component, they will never make cycles. So in plants can be represented by topological information that is called a tree structure, which is a graph plus, so tree, equal graph plus no cycle.
Couldn't we say even directed graph?
Yes, yes, you're right. We should say here plus rooted. And this I will just explain briefly. C'est pas bon, hein? And again, I explain briefly because it may be important for the rest. This is a tree because there is no cycle. However, you cannot tell me which tree is it if you think in terms of that a tree that should have a root. There is a main element that is anchored in the soil, let's say for plants, that is unique. Where would be the root here? Where would be the origin of this tree? The first element. Well, if I don't give it to you, you don't know. Could be here. But it could be here as well. Each time, it doesn't change the fact that there is no cycle, but it changed the origin. So a graph that is a tree with no cycle, for which you give a specific node that corresponds to the root, we call this the root of the tree, is called the rooted tree. And actually, this is exactly what we are going to use to represent plants. For instance, here, just by intuition, you guess that the root is here. But it might have been here, the origin of the. So this could have been this part that is connected to the other ones. So in order to give you the complete information about my tree, I need to give you what is the specific node in the. So for instance, here I would say my specific origin is here. And by this, I am giving you the root of the tree. And if I give you the root of the tree, it is equivalent to orienting the tree in the direction of the reading of the edges. As soon as I give the root, I give an orientation on all the edges of the tree, from the root to the other ones. And then I can thank you, David, for the question. And then I can redraw this in a more, let's say this one. So this tree hits this one, which is here. This one is two nodes that are here. And on the first one, there are two nodes. Like this. And now I have a rooted tree, which is equivalent to a directed tree. So this and this are equivalent. And with plants, we are going to consider directed tree graphs, always. Okay? In genome analysis, no, sorry, in the genome. In phylogenetic analysis, the type of trees that they are considering many times are non-rooted trees for different reasons. But there are places where it is important to have this notion of non-rooted trees. Okay. With the geometry representation of the plant, what it will be used for? Well, it will be useful for the interaction of the plant with the context. Light, for instance. Or for a root system would be water. It is the geometry that will be the interface between the outside and the plant. I don't need the topology to compute the light that is intercepted by the plant, as we said before. I don't need the topology. Why would topology be important? Topology would be important for transfer of information in the general sense. Like, for instance, if I want to model the transport of water, transport of carbon, transport of nitrogen, I would need to know where are the connections between the different elements, otherwise I cannot decide how it is transported. Okay? Now, so I schematized a plant structure here with different modules, with different names that I number to make indexes that I make it possible to recognize, identify. In order to represent this, as we just said, we are going to use a directed tree graph. I often use tree graph because tree is a bit confusing with botanical tree. So I say graph after that. But from the context, it can be very easy to understand. So this is the tree that I'm going to a tree graph that I'm going to use. And we can distinguish also there are a number of types of trees. So we said that there are rooted trees or directed trees, non-rooted trees, but there are also other types. Two important types. So here is the rooted tree, and here is a subcategory of rooted trees, which is called axial tree. And the axial tree have this property that for each node, so let's use this one. So I have my rooted tree here, and for each node, when there are two children to the node, I will choose two or three. I will choose always one which is special. So for instance, this one has one node, so this one will be special. So I indicate this by a green arrow. This one has two children, so I will choose one of the two to be special. I take this one. And this one has two, so I choose one to be special. You see that this determines particular paths in the graph, and this path will correspond to the stem of plants. Okay, so for instance, here you see that there is a main stem here that seems to appear. If I have a graph without this type of information, how can I retrieve this notion that this is a stem? You see it because it's geometric on the graph. But as soon as I go here, it starts not to be so obvious. So you need to have this type of notion where you indicate each time, if you have two choice, what is the preferred path. Okay? So this is called an axial tree. So here in red, you see, for each node in the tree, for instance, this one, has two nodes that are not marked and one node that is marked to be the preferred one. Okay? If this property is true for every node, then I have an actual tree. What we are going to use in the computer are actual tree representation of plants. So it's important really to get this notion. It won't be so difficult because after that it will be natural to, I mean, you will forget that even that you are using actual trees. But you need to know what they are. And I repeat, actual is meant to represent actually this notion of axis in plants. Okay, what are the nodes that are on the preferred path? In a plant, yes, to make the final... in a plant, imagine that I have a segment like this, which would be represented by another segment and another segment. And then I have a born segment, which is a lateral branch here. If I represented this by a node, I need to say that this segment will be the preferred one compared to this one in my graph to explicitly say that this segment is the follow-up of this segment on the axis, on the botanical axis. Okay? If I don't indicate this, I cannot tell because I have no geometric information. Because I need to draw the things. I give you geometric information here. But actually in the computer, you don't have the geometric information. So you won't be able to make the difference between this segment and this one. And therefore, you don't know where are the axes. Okay? So actual tree means trying to track the botanical axis within the plant structure. What? No, and I will go quickly on this because it will be a bit an aside with respect to what we are going to do, but you need to at least know that it exists. Plants can be represented by actual trees. There is, if you want to represent general plants, you need to have a bit more general notion because it may be that not only one modularity exists on a plant, like for instance, you want to decompose the plant in internodes, to chop the plant in internodes. You may want also at the same time to represent the plant at the level of axis and maybe at the level of groundlets because you don't use the same information at the different levels. So in order to represent all the types, so for instance here, you have an axis that is made of leaves. So there is a modularity that is the modularity of internodes. But a full module will be made of different shoots, growth units. Here, when you compute this, the modules, they will stack upon each other to build up the main axis of the plant. So a main axis here is made of modules, which is made of internodes. And here, in the end, you have the full crownlets that are made of these big axes, etc. So you see that there is a nested decomposition of the plant structure. How to represent this? The tree structure that I presented is not enough. Because the tree structure would be a modularity at a single level. So in order to represent this, we designed, like some time ago, the possibility to group the nodes into clusters so that the grouping, when you collapse every element of one group into one node, like for instance, this structure here would be collapsed into one, this still remains a tree. Due to this, by using this type of nesting formalism, you can describe trees at different levels, like nested dolls, you know. Okay, so this is one modularity. You can even add another modularity and even another modularity. And in the end, you end up, this structure actually represents different modularities, each one being a tree of the same plant. And here with this, we showed in a way by looking at different ways of representing plants, that we have a very generic structure, mathematical structure, to represent the architecture of the plant. And this is called MTGs for multiscale tree graphs. It is possible to manipulate MTGs in LPy, but we won't do it in this training session. So this is to a recap. Trees can be looked at different scales: internodes, modules, units, axis. Yes, internodes, unit, axis, and you can gather every description on a single object that is called MTG, and that looks like a nested set of trees. Now, if you want to link the topology and the geometry, how do you do? Because we have two types of representation. Okay? For the moment, we have no connection between the two. How do we do? Well, it's very simple. You said that for each node, so a node basically corresponds to a particular entity in the plant, particular botanical entity in the plant. It means that a node has a certain geometric geometric model associated to it. Okay? So if I want to represent this node, I would choose a model, a geometric model, and then attach information that makes it possible to position the element in the tree. And by this, I have, you see, if I do this, I attach attributes, let's say geometrical attributes to my graph. I'm able to compute both the topology of the plant and the geometry of the plant at the same time, with the same, let's say, computational object. And this makes it possible to recompute this, but if you change either the level or the geometric object that are attached to the different nodes, you can give completely different representation of the object, okay, depending on how you played with this combination. Okay? So this can be used at different scales. Using this MTG formalism, you would attach different geometries of the different nodes, but also at the different scales, which makes it possible to represent the plant both at a single scale, but also at multiple scale, and in a way that the geometry at the different scales are consistent. Because, for instance, here I chose at this level, let's say, to represent this set by a certain envelope, but you see that I need to have some sort of connection between the two layers because they represent the same reality behind. Okay, so the geometric model cannot be whatever in connection with each other. They must be linked. Okay, so I don't enter into the details how we do this, but
and it looks like it would be interesting, for example, for computer graphics.
Yeah.
And do you know if they use similar structures in computer graphics?
Yes, people are using level of detail formalisms. Do you want to say something about this?
No, just I was about to say,
Yeah.
for example, to render
Yeah.
far
Yeah.
objects.
Yeah. So, for instance, still in the world of plants, in many games nowadays, if you're far from the object, you have a representation of the object with a billboard, which is an image, let's say, to avoid entering in the details of the object structure. But if you get closer to the object, then you need to see more precisely the branches. And even when you rotate around, you need to see how you rotate around the branch. Then you need to switch the representation and have a more detailed representation, probably not as an image, but as a series of images or as a 3D model. And there are many areas where people are using this type of multi-scale representation, multi-level representation. Okay. So we are almost there. Tired? Still alive? I'm thinking of you because just after lunch like this, it might be a bit... No other question? Okay, so now that we now we have a sort of way to formally represent the plant architecture. Aha, but these are geometric things, graphs that represent topology, but it's not a string. We were speaking about string to represent the object in order to reuse this notion of string rewriting system, L system. So we still need to make this leap. So how do we represent plant architecture in terms of strings? Well, this is not so difficult because there is a well-known notion in computer science that says that every tree can be represented by a string. And it's very easy. You just need to add parentheses to the string. So if you have a tree like this, each time you encounter a bifurcation in the tree, you open a parenthesis. So for instance, here the B leads to a C and to a G. And I say that the B leads to a C. So I open a parenthesis. I close the parenthesis here. So everything that is in between is at a single level. And then the B is also connected to the next parenthesis, which is the C. And then I close the parenthesis here. So basically, this means that this B is below this part and below this part. Okay? And this is extremely general. And you can use this type of convention recursively because obviously G will be exactly in the same situation. G is below this one. H is below J and I. And you see that H is below J and I. Okay? So by using this parenthesis mechanism, then you can describe any tree in a linear manner. This is the point.
It's not unique for computation.
Sorry?
It's not unique. You can.
Yes, yes, you're right. So this, you are asking the right questions. It's not unique. The point is that I forgot to say there are other. I said before there are many types of trees. With some trees, the order of the children are important. With some other trees, other class of trees, the order of the children are not important. So, for instance, I think it is important. I use your question to go a bit deeper in some places. This is a tree, and this is another tree. Can you tell me whether these trees are different? Apart from the fact that... They look pretty the same. Actually, they could be, but they are not, because in my mind, this is the first children, because I wrote this on a board. This is the first and this is the second. And my first is here and my second is here for this tree. And this was in my head. Okay. So these two trees, because I decide, because I am the user, I am the one that is making the model, I decide that the order of the children is important. These two trees are not the same. If I count the order and if I tell you which is which. If now I decide that the order, because I wrote this one on the left and this one on the right, but here I wrote this one on the right, the left, and for the other one on the right, I switched the order. If I decide that it's not important to pay attention to the order, then these two trees are equivalent. So depending on the class of trees in which you are, it may be that the order is important. And in this case, it's ambiguous notation. It's not non-ambiguous. Okay? But if I decide that the order is not important, then this notation is absolutely perfect and is one-to-one with the tree. Okay? So what are we going to use for plants? Well, we could use both. And it's up to you to decide whether you want to take into account the order of the children or not. Most of the time, we take this into account, but it's not a necessity. In actual tree, this notation solves the problems, at least partly the problem of ambiguity here, and also reduces the complexity of the notation if I decide that for each red arrow that was the preferred direction, the preferred children, I don't need to put the bracket. So A is before B, A is before B. I don't open a bracket like here because B is my preferred children. So I consider that this is at the same level as me. So I don't need to open a bracket. And if I do this for all throughout the tree, I end up with a much simplified notation compared to the previous one. Okay? And actually, this is very close to the way we designed this like 20 years ago or so, to the way biologists are really writing in their notebook the plants. It's not exactly this, but it's very close to. Because it's compact, it's simplified compared to the full extended notation. And also, it is compatible with the notation that we are going to use for LPy and the programming of these plants. So here, what I wanted to say. Yes, to show you the parentheses, how it works. So A, B, C, D, and E are on the same axis. Once, if you remove all the parentheses, I open and I close here. If you don't consider the inside, it remains A, B, C, D, A, B, C, D. And if you don't consider the F, you have A, B, C, D, E. And you see the axis. You see the main axis. And similarly with this, G, H, I, you look like here. G, H, you get rid of the inner structure that is lateral. And you have G, H, I, G, H, I. So you see how it works, the notation? Questions? One important thing to note is that for a string like this, so can I take any string, put parentheses anywhere, and get a tree? Answer is no. Because for this to represent a tree, you need that the parentheses are well bracketed. And this is called a weld form representation or formula. Okay? So it means that if I enter a subtree, I need to exit the subtree. If I don't exit, it means that something is missing.
The number of right, I don't know if you right brackets, right-oriented is equal to the left-oriented.
Yes, exactly. For each of the right-oriented square bracket, you find a balanced squared left-oriented bracket. Okay. So for a branching structure, so here we are closer to what we could see on the field. You would represent each segment of the plant, can be a unit, a gross unit, can be an internode, can be an axis. You would represent for each of the elements that you chose a node. Okay, B would be represented by a node, etc. And then you represent the connection between the node that are the segments that are physically connected on the plant. You put an edges between the two, and you put the red arrow corresponding to the different for the entities that are successively on the same axis. Just for you to notice, it is possible to do exactly the same game with multiscale tree graph, which means if you want to have even more complex models integrating several scales at a time, you have this type of model. And then the question is it still possible to represent this object with a tree? Answer is yes. And the object will be represented in this way. There is a bit of strategy. I don't want to enter into the details, but this can still be represented by a tree. So a tree graph has also the nice multiscale tree graph has also the nice property to being able to be represented by a string structure. Okay.